Hello, and thank you for participating in the summit. Today, we're going to talk to you about a case study that the Uown Education Committee members are in the process of developing. Those members include myself, Deb Dooley, Julia Schmitz, Bruno Geary, and Riley Farrell. Next slide, please. So what is Uown? For those of you unfamiliar, Uown is an all-volunteer organization consisting of citizen scientists and advocates that work towards the protection of the Upper Oconee Watershed Network. They've been operating for over 20 years and been collecting data quarterly over that period of time. Uown has several goals that include monitoring and science, as previously mentioned, advocacy, that is making sure that our surface waterways are protected, education, providing those in our community with educational resources so that they can share those, and also recreation. Next slide, please. So the purpose of today's presentation is to talk about a case study that the Uown Education Committee is in the process of developing, as we are charged with serving as a resource for teachers at all levels, K-12 and beyond, and also making those connections between the data that Uown has been collecting over those 20 years to the educational community through research and application being a case study such as this. This case study is being developed for submission to the National Center for Case Study Teaching and Science that is administered through the University of Buffalo. We are developing it to be geared towards middle school through low-level undergraduate courses with some alterations or variations in approaches to administering this case study and providing the students either with the event or having them discover on their own what has occurred. We're using, again, the guidelines for the case study, and the type of study is analysis of data. Next slide, please. So through this study, we have to provide them with an encouraging or interesting or exciting introduction. How can we get the students engaged? So what color should water be? How do you know if it's the wrong color? Well, natural waters, as we know, can vary greatly in color. So having long-term monitoring is a good way of knowing when there's a problem and what is the potential impact of that problem. We use for this case study the chemical plant fire that occurred on Trail Creek, turning it a very vibrant blue in 2010. Now, Bruno's going to tell you a little bit about the parameters that we use to identify this occurrence. Bruno?
Thank you, Deb. Yeah, as Deb said, I'm going to tell you guys a little bit in terms of background about the parameters that we use to show the students and the data that we show the students so that they can think about what may have happened. And the first one, a very important one in chemical monitoring, is called conductivity. For those of you that are not already familiar, conductivity is basically the ability of a water sample to pass an electrical current. The higher the amount of dissolved ions in the sample, the higher the conductivity. And as you can see on the slide, it's measured easily with a handheld meter and reported in units of milli or microsiemens per centimeter. The range for waters in Georgia, surface waters, can be quite wide, between 50 and 1500 microsiemens per centimeter. In this area, in the Piedmont, it's typically on the low end. Volunteers measure the background levels and sort of figure out what a typical value is. And then when it changes with regular monitoring, you can sort of figure out that something's gone wrong. The things that will impact conductivity in a negative way are a variety of activities, mostly human. The number one which we are concerned with is urban runoff, but we also see issues with sewage leaks, and there is quite an impact from agriculture activities and also from mining operations. Next slide. The second parameter that we look at is called pH, most of which Most of you are probably already familiar with pH. It's a scale between 0 and 14. Between 0 and 1 reflects a change in the number of hydrogen ions by 10. So that's just a fancy way of saying the lower the pH, the more acidic a sample, the higher the pH, the more alkaline or basic a sample. In Georgia, the state standard for pH is that it be between 6 and 8.5. We see a variability down south where we can see pHs as low as 3.5 because of acid mine drainage is one of the reasons, but also the presence of long organic acids, such as humic and tannic acids. Close to water, the pH can be a little higher, mostly because of salts. The significance of pH measurement is that aquatic organisms are very sensitive to changes in pH, and a very small change in pH can cause negative effects in that environment. Next slide, please. The third parameter I'm going to talk about is biological score. And that is something that comes from Georgia adaptive stream methodology. And it comes from sampling for what we call macroinvertebrates, which are essentially baby bugs that live in the environment. And they are amenable to monitoring because they can be sorted by sensitivity to pollution. As you can see, there's 4 pictures on my slide. All of them are different in terms of their sensitivity to pollution. So when we sample the community of macroinvertebrates, it tells us something about how healthy the environment is. And when we're done calculating the score, we can grade it between poor and excellent. Next slide.
Thank you, Bruno. I'm going to talk about the last 2 parameters, which are E. coli and turbidity. E. coli is a bacteria, and it's something that we monitor monthly because it can show us quickly there's a health risk due to contamination of the surface waters. There's a high amount of E. coli, most probably means that there's a high number of fecal coliforms. Fecal coliforms are bacteria found in the intestinal tracts of humans and other warm-blooded animals. These could be pathogenic and could cause disease to humans, animals, or plants. But not all bacteria are bad. Some bacteria can play a beneficial role in the water. They can help with decomposition of plants, where they consume dissolved oxygen for respiration, nutrient cycling, which ensures turnover of nutrients that benefits the plants in the soil, and pollution control, as bacteria have been used in oil spills and sewage treatment. In the picture on the slide, you can see how you actually monitor for E. coli. So you're looking for the blue colonies that are in the gas bubbles on the petrofilm. The sources of E. coli in our water could come from wildlife, livestock, urban storm runoff, leaking pipes, or failing septic systems. The recommended levels based off the EPA depend on what type of swimming is done in there. So if it's a designated swimming area, you expect to see 235 colony forming units per milliliter or less. Moderate swimming, you would see 298. Light swimming, you would expect there to be 410 CFU or less. And infrequent swimming areas can be as high as 576 CFU per milliliter or less than that. And these levels correspond with an accepted risk of 8 people per 1,000 people getting sick. Turbidity is how clear the water is and how much light scatters when you shine it into the water. So the higher the intensity of scattered light, the higher the turbidity. So you can see in this picture here, the one that's at 50, you can see pretty clearly through the glass if you were to hold it up. Whereas you increase in turbidity going all the way up to 1,000, you can see that the water looks murky and that you can't see through it. This isn't good for the plants and things that live in the water. And the material that can affect the turbidity could be clay, silt, algae, organic matter, inorganic matter, and microscopic organisms like we were just talking about with E. coli. So the higher the turbidity of the water, the potential there is of pollution in that body of water, and we would need to figure out what is causing that turbidity for the water.
Thanks, Julia. After students have been explained each of the parameters of interest, we have a series of plots that we show them for them to analyze. We happen to choose biological score for the sake of this presentation because it's an easy one to analyze, but not all of the parameters of interest that Uown has monitored for actually see much of a shift before and after the chemical spill. We want students to parse through this data and learn how to actually evaluate real data as opposed to just being given a data set that have really easy to see trends. We want them to actually be able to discern which variables they can draw conclusions from and which they can't. So for a given plot, we would want them to make a series of observations. For biological score, those can be, for example, the y-axis, how it's different between Trail Creek and Bear Creek, indicating that in general, Bear Creek is a more biologically healthy system than Trail Creek. You can also, from these plots, observe that there was a discernible decrease in biological score immediately following the chemical spill in Trail Creek, but none in Bear Creek, the reference stream. And you can also see a defined recovery period in the Trail Creek spill, showing that the creek actually is able to recover following the disturbance. Next slide, please. Students can use the plots that we show them to come up with a series of takeaways. As long as those takeaways are actually supported by the data, it doesn't particularly matter what the students say. Some examples might be that Bear Creek in general is a healthier stream because it's more stable and generally has healthier ranges for each of the parameters of interest, or perhaps that Trail Creek has a defined shift in many of the variables immediately following the spill, followed by a recovery of those variables. And we're particularly talking about the biological score and the turbidity, which you can notice those shifts. As long as students can back up their takeaway, it doesn't particularly matter what it is. Next slide, please. All right, and then from those, like the data analysis, we basically just want students to be able to know that they can actually use citizen science data to support arguments, and that data is important, and also that there actually are impacts from human land use on a given ecosystem, but that these impacts aren't necessarily permanent, and that through action, whether that's remediation or something else, ecosystems can recover from degradation. And that is what we want students to take away from this case study as a whole. Thank you.